Incline planes. Now, this is our last section for this unit, and I'm not going to lie, it's pretty much exactly the same as what we've been doing all this time with free body diagrams and equations and stuff, but there's just a very slight twist. Now, an inclined plane, that is just a fancy way of saying a ramp. Okay, a ramp or a hill or any type of incline at an angle, that is what an inclined plane is. It's a ramp. Uh, that's all we're going to look at is what happens when motion happens on a ramp. Now, if we think about a ramp, either you are applying a force to climb up the ramp, or you are letting an object slide down the ramp like a slide. So that's what we're going to look at. Now, this first page, we're going to talk about in class, about simple machines and stuff. But I'm going to use this space just to explain why you actually already know how to do inclined planes. So to start with, I'm going to look at a flat ground, normal, free body diagram experiment. Let's just say here's an object, okay? We have our normal force of gravity being pushed down with the normal force going straight up. And let's just say, for sake of argument, for this example, we've got an applied force going to the right, and we've got the force of friction going to the left, okay? Now, if we wanted to look at this equation, we might say that the sum of the forces in the x direction, right? Here is our x direction, here is our y direction, x going left and right, y going up and down. The sum of the forces in the x direction being Fa minus the force of friction, and the sum of the forces in the y direction being Fn minus Fg. Cool, nothing special about that. Now, I'm going to do something cool. I'm going to take this exact same picture, and I'm going to copy it over here, okay? But now, I'm going to make this the ramp side, okay? Now it's a ramp. Now, in order for me to make this into a ramp, I need to take this entire picture and rotate it to be at a ramp, at an angle. So now we have some, if I just draw the horizontal dotted line here, we have some angle theta there. That is the angle of incline. Okay, maybe it's small, maybe it's big. That is our angle. So when we do this, a couple things change. We don't have the x and y direction anymore, okay? Because our x and y direction, if we think about it, x is horizontal like this, and y is vertical like this. But now we've got this weird angle, so our vertical line and our horizontal line doesn't really match up nicely with our incline. So instead what we do is we call it the parallel direction and the perpendicular direction. And this parallel direction goes up and down the surface of the ramp, and the perpendicular direction goes up and down straight out the surface of the ramp. Perpendicular 90 degrees here to the surface of the ramp. So if we increase the angle of the ramp, well, our perpendicular direction is still just going 90 degrees out from the surface of the ramp. So all this other stuff changes all this other stuff, stays exactly the same, where we might look at, instead of the x and y direction, we would look at the sum of the forces in the parallel direction. And what that gives us, in this case, again, it would be Fa minus the force of friction, or the sum of the forces in the perpendicular direction being Fn minus Fg. Now, I'm not going to lie. This right here is not awesome. There's some extra things to this that we are going to look at on the next page, but that is the general idea of how these things work. Because what happens is this force of gravity is no longer straight down. If you think about the force of gravity, that is the force hanging straight down, which means our new force of gravity is actually going straight down like this. That is what the new force of gravity compared to the old flat ground. So we don't actually, we don't like this old force of gravity anymore. So we need a way to figure out, well, what does this force of gravity actually do? So let's look a little bit closer at that. Now on this next page, really, the entire magic of inclined planes is the fact that the force of gravity, when you're sitting on the ground, all of its weight goes into friction. Everything is going right into the ground. But when you sit on a ramp, okay, some of that weight pushes the object down the ramp, right? Gravity is bringing that object sliding down a ramp. That's why slides at playgrounds work, because gravity is bringing the object down the ramp. Instead of it just free falling straight down, we are slowly guiding it over a longer distance down the ramp. Now, not all of the weight, that force of gravity, goes into sliding down the ramp. There is still some of it going into friction. And when it goes into friction like that, that pushes the object against the ramp, right? It's pushing against the ramp to create friction. So what does this look like? Well, what we actually have here is our force of gravity going straight down, like so. This right here is our force of gravity, which is equal to mass times gravity. Now, what we have, which is kind of cool, and I'm going to move this over to the other side like this, and what we have is a nice, now we care about the perpendicular direction, right? So what we're going to call this purple arrow right here, I'm going to call this F perpendicular. And what this is the component of gravity. I'll say this right here is gravity pushing into the ramp, okay? Into the ramp. So that's gravity pushing into the ramp. Now, if we look at this orange component that goes like this, now if you notice, this orange component is actually the component that's perfectly parallel right here to the surface of the ramp, which means we're going to call this F parallel. And F parallel is our gravity pushing down the ramp, okay? Down the ramp. So we have our two components. We have F perpendicular that goes into the ramp, and we have F parallel that is gravity pushing down the ramp, okay? Now, you're gonna have to trust me with this one. The angle of this beautiful triangle that we just made, if we have some angle theta that our ramp's at, that angle exists right there. Now, if you really want me to prove it to you, I can do the cheap way. Take this triangle. I will just get the triangle here like this. Take it, rotate it. Look at that. It is exactly the same, but just flipped. There's our triangle. We go like that. We go like that. It's exactly the same angle. Just trust me on that. You don't have to really memorize this picture right here. But what you do need to memorize and recognize is that we are dealing with a 90-degree angle right here. This is a right angled triangle that has a hypotenuse equal to mass times gravity, to our force of gravity. So if we look at this thing, okay, we have our two components. We have our F perpendicular, the component of the object's weight that's perpendicular to the plane. Now, if we look at this, this trigonometry, we're going to assume that we know what the force of gravity is, that we're given the mass, we know gravity, that's totally cool. Which means if we look at the cosine of this theta, we're going to get F perpendicular divided by mg, our force of gravity. I could even color code that a little bit if that helps. I can turn that green. This is our force of gravity, which means if we take this, we can solve for the fact that F perpendicular is mg times the cos of our angle theta. That is the perpendicular force of gravity pushing this thing perpendicular. And when I say perpendicular, I mean into the plane. If we do exactly the same thing, but for this orange component with our F parallel, well, again, looking at our triangle, we are dealing with the opposite side and the hypotenuse, which means if we look at the sine of the angle theta, we're going to get F parallel divided by our force of gravity, which exact same idea. Our F parallel is going to be mg times the sine of theta, and that is our object weight that is parallel to the plane. And when I say parallel, I mean it's going to push it down the ramp. Okay, these two formulas right here, we'll box them, we'll highlight them. That is fantastic. You need to memorize these formulas. You're going to do enough practice that you need to memorize. Oh my goodness, you can't even read that with the orange highlighter. Let's just do it in green, I guess. There, that's better. Okay, these two formulas right here, you must memorize. Okay, memorize. Yes, this is an online course, so I don't really give you a formula sheet, but if otherwise you need to know these. You're going to do enough practice that you will know that F perpendicular mg cos theta, F parallel is mg sine theta. Okay. Now there's a very distinction about F parallel. Okay, which I'm going to reiterate many times. F parallel is always down the ramp. Always. Gravity is never going to push an object up the ramp. If you just put something on a ramp or a hill, that object will never, ever go up the ramp unless you apply a force to it. F parallel always exists. It's like the force of gravity, but it's the force of gravity that's pushing that object down the ramp. Okay? Now, if you have friction, okay, again, friction will depend on the motion of the object. If the object is moving up the ramp, then friction is acting down the ramp. If the object is moving down the ramp, that means friction goes up the ramp. Opposite of the motion, exactly the same as before. Now, when you solve these problems, okay, you're going to do exactly the same thing. You're going to draw a free body diagram, okay? Always. That's no big deal. But now, this free body diagram is going to be on an angle. That's totally cool. I don't like how thick that line is. So let's go. This free body diagram is going to be on an angle, like so. Perfect. Okay. But what you need to do is you must define which way is positive, up or down the ramp. And what you're going to do is you're always going to set positive, the positive direction, to be matching the motion of the object. Okay? If the object goes up the ramp, you set up to be positive. If the object moves down the ramp, you set down to be positive. If you're unsure, take your best guess, and the math will tell you with either a positive or negative acceleration. But it will make your life way easier if you're setting the positive direction to match the motion of the object. Okay? And once you've done that, the same old, right? Now you are doing your F parallel and F perpendicular. This is like, it's not exactly the same, but it's like your sum of the forces in the X direction and sum of the forces in the Y direction. It's exactly the same. And all of the solving of the equations and everything else is just like before. Okay? Just like before. Everything else is exactly the same thing. Now, you must keep one very big distinction here, is you must remember that having an object sitting on an incline is not the same thing as pulling at an angle, okay? There are two very different things. I'm going to do it in red right here. Two very different things, as if you had a box. Oh, that is not a box. If you have a box like so, and you are pulling at an angle with some applied force, that is not the same thing as having a box that is sitting on an incline. Okay? Very important that you know the distinction between the both. This one has parallel and perpendicular. this has X and Y, okay? Make sure you know the difference, make sure you don't get them confused. Let's do an example or two. I don't want this video to be too long, but let's kind of get you warmed up a little bit and let's see what happens here. Okay, so we've got a 15 kilogram box sitting on a ramp with an angle of 24 degrees. So our free body diagram, what I'm gonna do with this, okay, I'm gonna draw a ramp like so. I'm gonna put our box there. If you want, okay, you can draw a dotted line here and say, there's my angle, that's equal to 24 degrees. That's totally cool. You don't even have to put the angle. You can literally just put the 24 degrees in the corner there. That's totally fine. Now, the two things that always exist, okay, always are F perpendicular and F parallel always exist in these types of questions, in ramp questions, okay? So right off the bat, before we even look at anything else that's happening, we are going to put our F parallel down the ramp, we'll call that F parallel, and we are going to put our F perpendicular going down like this, and our matching F perpendicular is going to be the normal force going up, like so. Okay, now I'm going to put it in red. This normal force is not like that. Okay, not straight up and down. It is perpendicular to the surface. Okay, we should have a nice 90-degree angle right there. So there we go. That's all that's happening here. Okay, now this object, okay, is it going to move up or down the ramp? Well, if anything, the object will slide down the ramp. Okay, so therefore, we're going to put down as our positive direction. So we're going to say down this way is positive. It's crucial that you have this distinction here, okay? Because when we now, okay, if we want to figure out, well, what components of force is acting down the ramp, okay, that down the ramp component is going to be our F parallel is what's happening down the ramp, okay? Which means, and our F parallel, we're really, really good. We've memorized this already. This is mg sine theta. So if we go ahead and take our 15 kilogram box, we toss in our gravity of 9.81, and we toss in the sine of 24 degrees, we are going to get a nice, beautiful answer of 59.9 newtons. Cool, that's no problem. That's more of just a plug and chug. If we want to figure out the normal force acting on the box, okay, normal force, right, we need to look at the sum of the forces in the perpendicular direction. Just like when we wanted the normal force for regular flat questions, we need to look at the y direction. We need to look at the perpendicular direction. So the sum of the forces in the perpendicular direction, we have our normal force fighting against this perpendicular force, which is 0, which tells us that the normal force is equal to F perpendicular, which we know is mg cos theta. So if we go ahead, toss in our 15 kilograms, our 9, oh, that is not a 9.81. There's our 9.81 times the cos over 24 degrees. We get a normal force that is equal to 134.4 newtons. Okay, exactly like what we did before, but now we are working in a perpendicular direction. Now, some of the forces in the perpendicular direction, not just F perpendicular. This, right, F perpendicular and this F parallel, this exists no matter what. We are calling the sum of the forces in the perpendicular direction or the sum of the forces in the parallel direction just our X and Y. It's just our way of labeling things up and down the ramp, and it's not necessarily just F perpendicular and F parallel, okay? So if we look at another type of example, okay, exactly the same question, but let's figure out this dog accelerating down a giant hill. This dog is tobogganing. So we've got a hill incline at 25 degrees. What's the dog's acceleration down the hill? Now, if this sounds just like the last question, you're right, because it is. We've got a nice doggo, which is a box sitting on a hill. Always, always, always F parallel going down the ramp, F perpendicular being pushed into it, okay? How I like to think about it is this F parallel and F perpendicular, okay? That is in lieu of our force of gravity. Notice how we don't have the force of gravity anymore. Instead of the force of gravity, we have F parallel and F perpendicular. If we were to take this and we were to rotate it to a flat ground, now all of a sudden these two things disappear and we have the force of gravity again, okay? But if we take this and rotate it back up, our force of gravity disappears and we get these two components, F parallel and F perpendicular. We forgot one last thing, the beautiful normal force going straight out like so. Because we have contact, this dog is not flying, so there is our normal force. So acceleration down the hill, okay? This thing is going to slide down the hill, so we define down as positive, which means we need to look at the fact, what are the sum of the forces in the parallel direction? The only force that's acting in the parallel direction is this F parallel force. So the only force there is F parallel. Now, for sake of argument, if we had friction, okay, this friction goes up like this, which means now we would have F parallel minus the force of friction, just like we did before. We don't have friction though, so we don't have to worry about that. Instead, we can just say that the sum of the forces in the parallel direction, F parallel, is equal to mass times acceleration. Now, oh my goodness, we didn't even realize there is no mass given. Is that a problem? Maybe, but with inclined planes, something magical happens. If there is no mass given to you, then the mass must cancel. Okay, mass cancels out. It will always, always, always cancel out. Now, if we look at this a little bit closer, right now it doesn't cancel out, but if we plug in mg sine theta for F parallel equals ma, oh my goodness, I told you so, right? Now in this step, we have mass on both sides, divide out by mass. We just have g sine theta equaling the acceleration down the ramp. Oh my goodness, it's magical. Well, this acceleration is just 9.81 times the sine of 25 degrees, which means this acceleration down the ramp is just 4.1 meters per second squared down the ramp. Now, if you forgot and you said up the ramp was positive, that's no big deal. This 4.1 would be negative. That's it. Okay? Now, that's cool. How fast is dog going when it slides 35 meters to the bottom of the hill? This sounds like kinematics. You're right. This is just kinematics, but on an angle. Does that change anything? Nope. It's exactly the same. Okay? Yes, our motion is going on an angle, but who cares? Okay? We have a distance of 35 meters. We have an acceleration of 4.1 meters per second squared. We have an initial velocity of 0 meters per second, and we want to know what our final velocity is. So all we need to do is say, well, v final squared is equal to v initial squared plus 2ad. We don't care at all about time because we have an initial velocity of 0. That's beautiful. So our final velocity, that is not the right color blue. Oh my goodness. This is right here. Our final velocity is just going to be the square root of 2 times our acceleration times d, which is just 2 times 4.1 times 35 meters, just a kinematics question, which means our final velocity is going to be a good old whopping 16.9 meters per second. Just regular kinematics. See, I told you you knew how to do this stuff already because all we're doing is taking a regular flat question, say something like this, something like this. Now we don't need an applied force to create motion. All we need is an angle. We get F parallel, and this thing starts sliding down the ramp. It's beautiful, okay? Now, I'm gonna stop here. We have 1, 2, 3, 4 examples left. We'll go through a couple of them tomorrow in class. Feel free, jump forward and try them. This question number 3 may be slightly more challenging, slightly different. Maybe don't do it. I would suggest try question number 4, okay? This is the same as number 2, except with friction. It's exactly the same, but now we have friction, so you can try it, figure out the acceleration, okay? And now we're asking how fast are they going after 8 seconds. So I give you a time instead of a distance, but it's exactly the same question, okay? So try those questions. Hope this video was helpful. We'll go over the rest of these in class tomorrow, and I will see you later.